All right, let's talk about the stereochemical outcomes of E1 and E2 reactions. And so we talked about the stereochemistry outcomes of SN1 and SN2 reactions. We saw that in SN1 reactions, if we start with one chiral enantiomer as a starting material, then we get a racemic mixture in our product because we generate a carbocation. Carbocations are flat. But in SN2 reactions, we see that we have to have backside attacks, so our nucleophile has to attack as the leaving group leaves, and so we're forced to get the opposite enantiomer of whatever we started with. In E1 and E2 reactions, we generate alkenes, and remember that we use E and Z to indicate the stereochemistry of an alkene. And so let's walk through an example here of an E1 reaction. And so if we look at our entire organic molecule, we want to identify the carbon that is partially positive and attached to a leaving group. So we look around and we see that this carbon right here is attached to a bromine, making it partially positive, and bromine is a good leaving group. And so this is where our reaction is going to occur. What type of carbon is this? It is secondary, and so it could undergo an E1 or an E2 reaction. We then need to look and see what's over top of the arrow. We see that we have water, and that is neutral, so that promotes an E1 reaction. And then we have this triangle down here, the delta symbol, which stands for heat, and so this all promotes an E1 reaction. So now we're ready to walk ourselves through the mechanism. The first step is our leaving group just pops off, so off goes the bromine. Remember that this is called heterolysis. And so the outcome of this is the generation of this secondary carbocation shown here. And so once that is formed, we now need to use our base and pull off a proton from the beta carbon. Remember, the carbocation is on this carbon right here, which we call the alpha carbon. We then look around for beta carbons that have hydrogens. There's no hydrogen over here on this beta carbon because remember that pH stands for phenyl. And then we look over here to this beta carbon and we see that there is indeed a hydrogen on this carbon. And so now we can take our base and we can pull off this proton. So we take water and we draw from electron rich, we grab the hydrogen, and we move these electrons down towards the carbocation. So the outcome of this is the generation of an alkene, and so we have our phenyl group down here connected to this carbon here, and then we just generated an alkene, and then we have our phenyl group pointing up over here. And then we also had this methyl group that was connected over here. So our final product would look something like this. And what type of alkene is this? It is, let's look on both sides. So we cut it down the middle. We're looking over here on the left-hand side. Does the methyl group or the phenyl group win? The phenyl group wins, so it gets priority 1. And then if we look over here on the right-hand side of the alkene, we see that phenyl is going to beat out the hydrogen here, so that would be priority 1. These two priorities are on opposite sides, and so we call this E. But if we go back to this carbocation intermediate shown here, so after the bromine popped off, we're back to this point. We do have free rotation about single bonds, and so we can have this rotate around 180 degrees. And so if we rotate 180, we would end up with something that looks like this. Where our phenyl group over on this carbon has rotated down. Now notice that these two phenyl groups are on the same side, and so once we do our elimination, our phenyl groups will end up on the same side of the alkene. In the previous example I just drew, the phenyl groups were pointed in opposite directions, and so that's why we got the E-alkene product. So let's finish off our mechanism here. We take our base, which is water. We grab this proton right here and move those electrons down towards the carbocation. And what is the outcome of this? Like I just mentioned, the phenyl groups are on the same side, and so they'll be on the same side of our alkene product. So something like that. And then don't forget your methyl group, which was up here. And so our final product would look something like this. We then want to look and see if this is E or Z, so we chop it down the middle. We look over here on the left, we see that phenyl is going to beat out our methyl group, so that gets priority 1. And then we look over here on the right-hand side of our alkene, and we see that phenyl is going to beat out the hydrogen, so that would get priority 1. These are on the same side of the alkene, and so we call it Z. Alright, so since we had a carbocation intermediate, we're able to rotate around the bond, and this gives us a mixture of both the E and the Z products. One of these is going to be favored over the other. Remember that phenyl groups are relatively large, and so if they're on the same side of the alkene, they're going to be bumping into each other, and they're not going to be very happy. And so in this case, we might obtain an uneven mixture of these two products, where the E alkene is going to be our major one due to steric hindrance of the phenyl groups. They want to be on opposite sides. And so if you're on an exam and I say draw all possible products, you draw both of these and then circle the major product, which would be the E one shown here. And so just like I mentioned in the SN1, SN2 reactions, is this a stereoselective process or a stereospecific process? It is stereoselective. Why do we call it a stereoselective process? It's because we have the option of making both the E and the Z diastereomers, but we select for one of those over the other due to steric hindrance preferences. All right, so E1 reactions give us a mixture of E and Z isomers, but E2 reactions provide the single isomer that results from the leaving group and the hydrogen on the beta carbon being anti to each other. And so this is very important. Keep this in mind when you're working through different problems. And so what does it mean by anti? Think back to Newman projections. So when did we talk about anti and Newman projections? Remember, a Newman projection looks something like this, where the dot is our front carbon, the circle is our back carbon, and then we have things coming off of those. So we draw lines that look like this. And remember that if we are talking about our hydrogen right here, it needs to be anti to our leaving group. And so it needs to have something like this, where they are 180 degrees apart from each other. All right, so let's look at this same molecule that we looked at earlier in our E1 reaction. And then let's walk through the thought process. Why is this an E2 reaction this time? So we identify that this carbon right here is attached to the bromine. Bromine's a good leaving group. It's also more electronegative than carbon. And so this is where our reaction is going to take place. We see that this carbon is secondary, so we could have either E1 or E2 occur. So we need to take a look at what is over top of the arrow. Remember that sodium doesn't mean anything, so we just mark that out. We put a negative charge on whatever it's next to. And so our base here is negatively charged, which promotes an E2 reaction. So let's walk ourselves through the thought process of the mechanism. So we need to identify where our leaving group is. That's right here on this carbon where this bromine's at. And then we need to look at the beta carbon and identify where the hydrogen is. So there's one right here, which I just drew in. And then we need these to be anti to each other in order for the reaction to occur. We see that both the hydrogen and the bromine are pointing out towards us, so they're probably not anti to each other right now. But let's go ahead and draw the Newman projection looking down this bond right here. And so if we put our dot in the middle, that represents this carbon. We then put a circle around it. This represents the back carbon back here. And then we see that the phenyl group is coming down on this front carbon, and that the H is coming out of the board. So if we're looking from over here, we see that it's going off to our right. The methyl group is going off to our left. I'm going to write CH3 so we don't get confused. And then on the back carbon, we see that the phenyl group is up in the plane, and that the bromine here, if we're looking, is going out towards our right. And then our hydrogen over here is going off to our left. All right, so let's identify where our leaving group is. Our leaving group is right here. And then on our, so it's attached to the circle in the back, which is our alpha carbon. And we go over to this dot in the front, which is our beta carbon. And then where's the hydrogen that we're trying to pull off? It is right here. These two things are currently gouged to each other, and so we need to rotate them so that they are anti. So if we rotate, let's go ahead and rotate the back carbon so that the bromine then becomes over here, and it'll be 180 degrees from this hydrogen. So I'm going to keep the front carbon the same. So here's our hydrogen right here. We still have phenyl down here. We have CH3 over here. And then our back carbon, we've rotated 120 degrees so that our bromine is over here. So bromine is now here. Our hydrogen is now up here. And our phenyl group is now down here where the bromine was. Now we look at our leaving group. It's this bromine right here. It's attached to the circle, which is our carbon with the leaving group. And then this dot right here represents our beta carbon. And here's the hydrogen that we're going to pull off. And so now this is in a conformation, an anti-conformation, where we can have our reaction occur. And so if we redraw this into the skeletal structure, so we went here to a Newman projection, rotated, and then we're going to go back to a zigzag structure. And so if we want to draw this out, we see that the phenyl and the hydrogen are in the plane of the board. And so we start with phenyl here, up to this carbon that is connected to, back to this back circle carbon, and then up to this hydrogen that's pointing right here. We then have something that is coming towards us off of this carbon, something that's going away, something that's coming towards us off of this carbon, and something that's going away. So let's look at our front carbon here. We see that our hydrogen is going off to our right, and so the wedge that's coming towards us is going towards our right. And then the CH3 group here is going away from us, so we drew it here. And then if we look at the back carbon, we see that hydrogen's up in the plane of the board. The phenyl group is going off to our right, and so that is going to be here. And then the bromine is going off to our left. So now we have something that looks like this. Our hydrogen on our beta carbon, again, is anti to our bromine. This must occur. Keep this in mind when you're working through E2 reactions. And so now we take our base, so we take tert butoxide, which is this molecule here. Remember that tert butoxide looks like this. So that's what this looks like. And then this is a bulky base, so it comes in and grabs the hydrogen. These electrons move down, and we kick out our bromine in our bimolecular elimination step. So what does this give us? If we look, we see that the phenyl groups are on the same side, and so they're going to be on the same side of the alkene. So we get a final product that looks like this, and then don't forget your methyl group that was up here. So our final product would be this shown here. Is this E or Z? We chop it down the middle. We look on each side. So if we look at the left, we see that phenyl is going to beat out methyl group, making it priority 1. And then phenyl is going to beat out our hydrogen, making it priority 1. And so this alkene is Z. So we see that because of the stereochemistry of our starting material, we are forced to get the Z isomer here. And so what do we call this type of process? It is stereo specific, and we call it stereo specific because we don't have the option of getting E and Z here. We must get Z based on the stereochemistry of the starting material. Now this is only true in E2 reactions if the beta carbon, so the one containing the hydrogen that we're pulling off, is chiral. So this is only true in this case. Notice this carbon right here has 4 different things attached to it. So it is a chiral center, so it must proceed via a stereospecific process, only giving us the Z stereoisomer. So we proceed through an E2 mechanism, but the beta carbon is not a chiral center, so keyword not chiral center. Then there will be a mixture of E and Z isomers, so similar to what we saw with the E1 mechanism. So for example, we take this molecule we looked at earlier, except instead of having a methyl group here making this a chiral center, we now have 2 hydrogens, meaning it is not a chiral center. So let's go ahead and draw those hydrogens in here. And then remember, we also have 1 coming off of here. And so let's take a look at our Newman projection, looking down this bond where we look at our beta carbon from our leaving group as the front carbon. So if we draw our Newman projection, remember this dot in the middle represents this carbon. So it has a phenyl group coming down in the plane of the paper. And then it has hydrogens going off in both directions. We then look at the back carbon. We see that the phenyl group is coming up in the plane of the paper. We have the bromine pointing out, which means it's to our right, and the hydrogen pointing back, which means it's to our left. And so our Newman projection is shown here. We have 2 hydrogens on our beta carbon, and so I'm going to circle this one and put a square around this one so we can differentiate between the 2. We see that currently this hydrogen and the bromine are anti to each other, and so we could pull off this proton to get to our product. And so if we do that, we would just grab this proton back here. So we take our tert butoxide, because we know that potassium doesn't mean anything. It grabs this hydrogen right here, which is this one right here, and then we move these electrons down and we kick off the bromine. So what is the outcome of this? We see that the phenyl groups are opposite of each other. They're pointing in different directions, and so they're going to be on opposite sides of our alkene. So we draw out our product. We have something that looks like this, where one phenyl group is down, one phenyl group is up. So if we determine E and Z here, we would call this the E isomer. All right, so we saw that where we pulled off this circle hydrogen, the one that's going away from us up here, it's anti to our leaving group, and we get our E isomer as our product. Well, what about if we pull off this square proton shown here? That means we need to rotate it 120 degrees so that it can be anti to the bromine leaving group. And so I'm going to rotate the back carbon, leaving the front one alone. And so we rotate, again, leaving the front carbon alone. So I have an H over here that we squared, H over here that we circled, and a phenyl group coming down. Now I'm rotating my bromine over to here so that it can be anti to this hydrogen right here. And so my bromine is now here, my hydrogen is now up here, and my phenyl group is now over here. So now we see, after we've rotated 120 degrees, that our hydrogen over here is now anti to our bromine leaving group. So if we convert this back into a dash wedge structure, we see that our phenyl is down on the front carbon in the plane of the board. And so this carbon right here is this dot, It's then connected to the back circle here for this back carbon, and then hydrogen is coming up in the plane of the board. Now, on this carbon, we have something that is coming towards us, something that's going away, and the same for on this carbon. We just need to figure out what those things are. So on our front carbon, we have hydrogens going in both directions. So we plug those in here. And then on our back carbon, we see that our phenyl group is going towards our right, and so it's coming out of the paper. And our bromine is pointed to our left, and so it's going back behind the paper. So now we can see that once we take our base, or our terp-butoxide, shown here, we're going to grab this proton right here, which corresponds to this squared proton. Remember, before we grabbed the hydrogens going away. This time we're grabbing the hydrogens coming towards us because it's anti to this bromine. So we grab our hydrogen, we move those electrons down, and we kick off our bromine. What is the outcome of this reaction? We see that our phenyl groups are on the same side of the molecule as each other, and so they're going to be on the same side of the alkene. And so our alkene ends up looking like this shown here. If we figure out whether this is E or Z, we see that it is the Z isomer. So we see our outcomes from this reaction are that we get a mixture of both the E isomer as well as the Z isomer. And as you might predict, the E isomer is going to be our major product due to the steric repulsion of the two phenyl groups. This one is more stable and therefore would be our major product. So let's take a look at this practice problem shown here. So we look around our organic molecule, we identify the carbon that's partially positive and attached to a good leaving group. That is this one right here. We want to determine whether it's primary, secondary, or tertiary. It is a secondary carbon. And so we know that it can undergo E1, E2, or SN1 or SN2. So we want to take a look at what is over top of the arrow. We see that we have LDA. Remember that LDA stands for lithium diisopropylamide. Remember that lithium doesn't mean anything, and so we're just looking at this negative charge on the nitrogen right here. These isopropyl groups are bulky, and so this is a bulky base, meaning that we're going to undergo an E2 reaction. So now that we've figured out that it's going to be an E2 reaction, we need to walk ourselves through the mechanism. So we find the carbon that has the leaving group. It's right here. And so we call that the alpha carbon. And then we look for hydrogens on beta carbons. So we can go here. Here's one beta carbon. And here's the other beta carbon. So I'm going to draw in the hydrogens that are on these carbons. So since our methyl group right here is pointing away, that means our hydrogen right here is coming towards us. And then up here on this carbon, we have two hydrogens. So one is coming towards us and one is going away. And so we need to determine which protons we're going to need to pull off. Keep in mind, since we're doing an E2 reaction, the hydrogen that we pull off must be anti to our leaving group. So we see that our bromine here is pointing up out of the board towards us. We look over to this beta carbon here, and we might think that this would give us the more substituted alkene, which would be true, but is there a proton that is anti to our leaving group? No. Since this hydrogen is pointing up, this bromine is pointing up, and we can't rotate around this bond, this is not an option. We cannot pull off this proton. So our only option is to pull off protons from this beta carbon up here, since that we have one hydrogen going away from us, and it is anti to our bromine leaving group shown here. So now that we've identified which hydrogen we're pulling off, let's draw our mechanism arrows. And so we draw from our electron rich, grab our hydrogen, move those electrons down to make an alkene, and we kick off our bromine. So our final product would be this molecule shown here, where we have not touched this group over here, but we pulled a proton off here. Do not draw this as your product. Although this would be tri-substituted and this is di-substituted, we do not have a hydrogen here that is anti to our leaving group to pull off. And so this is not your answer, and this would be your final product.